Hey pre-calc, we're going to start in with mathematical induction. And what I want to happen here is just explore some deeper level math concepts. And there will be one of these induction problems on the test. So there's definitely a reason for you to want to figure it out. But it's also useful for any students that don't plan on taking the calculus route, but you still have to take math in college. And I think some of you will learn a little bit about how you can geometrically explain certain proofs, or not proofs, but certain sequences, and come up with an answer for this. So we've seen the sequence where we can do the sigma notation, n equals 1 to some number, or adding these numbers together. So for instance, what this is saying is that if n is 1, well, I guess I should be talking about k. If k is 1, then we're just adding 1 together, so there's one box. But if n equals 2, we start with, if k equals 2, then we start with n equals 1, and then we go to k equals 2. So 1 plus 2 equals 3. If we had k equals 3, so it would be 1 plus 2, and we stop once we get to k equals 3. So you can see there's a total of 6 here. So like there's one box, there's 3 boxes, there's 6 boxes, and I think you can see the pattern going on. There's 1 plus 2 plus 3 plus 4. So you can see that there's 10 boxes. And what I'm trying to get you to do is come up with a formula for any k value. And there's a reason why I put 2 boxes here, or like a repeat of figures, I should say. I guess I started to write out the sum here. So the sum of 1 plus 2 plus 3 was 6. The sum of 1 plus 2 plus 3 plus 4 is 10. And 1 plus 2 plus 3 plus 4 plus 5 gives me 15. The next sum, sorry about that. Well, the next sum would be 15 plus 6. And so what we basically need to do is come up with some sort of pattern to figure out what it would be at n equals 10 and n equals 100. And for some students, it's not that easy to just look at these numbers and see that there's a pattern going on. Well, based off of the picture, what I'd like for you to see is try to build 2 figures of equal size and try to make a rectangle. So what I'll do, and if this were a normal class, I'd probably have you try this on your own, but the nature of our class, we just have to do it this way. I'm going to stop at n equals 4. And the reason why I made 2 rectangles is because I wanted to copy the same figure on top. And you probably can't see it yet. So this box up here corresponds to this box. And these 2 boxes correspond to these 2. So I have the same exact image. I have 3 and 3, I have 4 and 4. So I have the same image. And so my thought process is, what if I find the area of a rectangle and then cut it in half? And so that's exactly what I'm going to do. I'm going to figure out, okay, well, what's the length of the base? Well, right now the length of the base is 4, but it's only a length of 4 because I did n equals 4 over here. Well, what's the length of the height? Well, from here, it happens to be exactly n high as well, but then I need to add 1 to it. So if I think about the area of a rectangle, it's equal to base times height, but remember, I only want half of it, because my blue figure is only half of that rectangle. So the formula that I'm going to come up with is 1/2 times the base of n times the height, which is not n, it's 1 more than n. And let's see if that formula works for what we have up here. Well, if n was 1, did I get a sum of 1? Okay, well, half of 1 times 1 plus 1 is 2. Well, half of 2 is 1, so the formula works there. If I plugged in n equals 2, half of 2 is 1. 2 plus 1 is 3. Is 1 times 3 3? Yeah. I can do it for 3 as well. Half of 3, okay, so 3 halves. And then 3 plus 1 would be 4. So 3 times 4 is 12, divided by 2 is 6. And so by using this formula, now I can actually figure out this sum right here, which would be 10 divided by 2 times 11, should be a sum of 55. Do the same thing with 100. And 100 plus 1. And you probably recognize this formula from what we did earlier in the school year. Yeah. So where are we getting to mathematical induction? This is just coming up with an equation. I like this visual, and I know it's very confusing. But the basis with mathematical induction is that we can come up with a formula. So here's my formula. And we should be able to prove that that formula works without using geometry, without drawing a picture. And basically what it is we set up all of these dominoes so that they are within range of each other. And then what we can do is we can just knock over the first domino, and then every pattern after that has to follow. Feel free to pause the video if you want a slightly different explanation. It's already written right here. And I'm going to show you how to prove this in the principle of mathematical induction. And again, I took this out of a math textbook, so this might make a little bit more sense. So basically what mathematical induction is we have this formula, whether we come up with it ourselves or we're given it, and we have to prove that it's true for the first one. I'm going to call this the base case. Oh, it's written right there. I think math people like the phrases that rhyme. And then you have to prove it for the next. So think of it as a domino. Like if it works for the first one, that's you touching it, and then you have to prove that it works for the second, which implies the third works, implies the fourth, the fifth, the sixth, so on and so forth. So I want to prove this formula that we've already come up with, 1 plus 2 plus 3 all the way to n. Let me write it down right here, 1 plus 2 plus 3 all the way to n is equal to this formula. Now I wrote it a little bit differently, but you should be okay with this. Yeah, I still wrote it differently than what it is up here. But I hope you guys all agree that that's equal. If you don't agree, please let me know. Okay, so what I do for the base case, there's two options. You can either just look at the first number. In this case, the first number is 1. Sometimes what I do, though, is I actually plug in the n equals 1 in for this part right here. Well, this is really easy because if I plug in n equals 1, I get 1. So that's my base case. What I need to do next is plug in n equals 1 on this side of the equation, here and here, and see if it equals the value over here. So if I plug in 1 and plug in 1, I'm looking at 1/2 times 2, and half of 2 is 1. And then usually what I do is I come up with a pretty straightforward sentence that just says, because 1 equals 1, the base case is true. I think I already made the answer key to your homework. I wrote out something like this. Since 1 equals 1, the base case is true. So now what I need to do is I need to set up my dominoes and I need to knock them down. So this is called the inductive step. And sometimes what I'll do is I'll even write this out. N equals k plus 1. So what I do is I rewrite the formula. 1 plus 2 plus 3 plus all the way until I get to the n, except now I change n to k. And I'm going to add one more step to it, and that is the next piece of the domino, and that's k plus 1. And some math teachers don't like to see this, but I like to write it down because it helps you know when to know to stop. So I write out WTS. It stands for I want to show or what to show. I don't remember what my professors used to call it, but you want to show that it equals the next term, not the solution up here. You want it to be, instead of n, k plus 1 over 2, and then this n, replace that with k plus 1 plus 1. So what I'm getting at is this equation worked for the base case, the very first domino. What I'm trying to show is that it works for the next domino, the k plus 1 domino. And I hope you are kind of understanding what I mean by the next one, because we've already done the sequences and series, that you understand that this means, or maybe I'll do this in a different color. I'll go back to red. And this is the next term, the next domino. So we already know, I'll switch back to green, that this equation worked for the first domino. So what I can do is I know that this equation worked for what was up here, this k over 2. And again, I'm using k's instead of n's because that's what we're working with. K plus 1. But I need to add the next domino, the next term to it. And I get to stop when I get this piece equal to what I want to show. Now, some people, before they do anything, they actually figure out what this want to show is equivalent to. And I think it's worth the while to write it out, that would be equal to k plus 2 times k plus 1 all over 2. And so you can actually look through this and say, okay, well, if I wanted these two things to be equal, you have a goal in mind. That maybe what you can do is start by, leave that as over 2 and distribute that k in there. So we're looking at k squared plus k. Maybe it would be worth your while to get this piece over here to have the same denominator. If you want to divide that by 2, you also want to multiply the numerator by 2, so distribute that in there. So we're looking at 2k plus 2 all over 2. And by doing that, you can see I'm getting the same denominator. So getting the same denominator, I have k squared plus 3k plus 2. And then look at the numerator. You can factor that to be k plus 1, k plus 2, all over 2. So essentially what we're doing is we took the first domino and added the next domino, and we proved that the formula still works for the next piece. I know this is very confusing, but this is the premise that we get. And I think I just wrote out, after this, I think I just wrote out the inductive step is true at this point. And this is a mathematical proof. By the way, sometimes a math person will put a little box here at the end. You might see that from me once I'm done with a proof. That's what we do. So I don't have enough time to do the next problem, so I'll see you in the next video. But we're going to practice coming up with a new formula. I'm not going to give you the formula. But what you'll actually see is the formula is actually down here already. And if you wanted to, you could actually try this on your own, try to come up with your own formula before I show you in the next video.